Thank you for coming to this talk. Attacks on cyber-physical systems are very common. Cyber-physical systems being connected to communication channels are vulnerable to cyber attacks. In particular, there could be different kinds of cyber attacks, such as spoofing attacks or integrity attacks. There could be denial of service attacks where the agents can be denied communications, access to data, or integrity attacks when false data can be injected into to system sensors or directly to the system actuators. So the motivation comes from the fact that CTS is vulnerable to cyber attacks. And there are several attacks in the past few years that have been very effective in disrupting the nominal operations of a cyber physical system. In particular, adversarial attacks can potentially lead to system failure, loss of money, as well as loss of human life. So it's required that fast and effective response are developed for safe operations of cyber physical systems. And we should be able to provide provable guarantees for safety critical missions so that we can guarantee that safety would never be violated even under adversarial attacks. Unfortunately, there are not many prior work that provide formal guarantees on safety, and the ones that do provide such guarantees, they generally rely on formal reachability analysis, which is computationally very expensive. So in this work, we consider a general class of non-linear dynamical system where some of the inputs are considered to be vulnerable or then can be attacked, and the rest of the inputs are secured that cannot be attacked. Here, the sets are considered defined as follows. So S denotes a safe set within which we require a dynamical system to remain at all times. And UV and US denotes the respective input constraint sets for the vulnerable and the secure input. And the function D models or represents the unmodeled dynamics or uncertainties in the system dynamics. The problem statement is as follows. We wish to design the secure input for the system such that the system trajectories remain inside the safe set at all times, starting from a set of initial condition X naught, and for any adversarial input signal coming from this set here. So as depicted in the figure, if the system trajectories start in the set X naught, they will remain in the set S at all times. And what we wish to design is a safe or secure input that can achieve that, and a set of initial conditions X naught from which safety is guaranteed. So our approach to solving this problem is as follows. So given the system with a safe set given as a zero subtype set of a function B, and the requirement that that set, the system trajectories remain in that set, we first identify which of these inputs are vulnerable and which of the inputs are secure. Then we develop CBF, or control barrier function-based safety conditions, which establishes existence of the vulnerable input constraint set as well as set of initial conditions. Then we develop a numerical method to actually compute these sets via sampling of the boundary. And after we compute these sets, we use them in a quadratic program framework or a QP with provable feasibility guarantees to design our feedback law. So let me start by reviewing the notion of robust control barrier functions. For this type of a nonlinear dynamical system, a function B is termed as a robust control barrier function if this inequality holds at each point on the boundary of the set S. And what it means is that if this blue region denotes the boundary of the set S, then satisfaction of this inequality means that the system trajectories point inwards when they're on the boundary, even in the presence of this unmodeled dynamics. And so the system trajectories can never leave the safe set S. And in turn, it means that if there exists a robust control barrier function or an RCBF, then the set S can be rendered formally invariant, which means that if the system trajectories start in that set S, they remain in the set S at all future times. So now we reformulate our CBF condition for systems under adversarial attack. So again, this is our system under division of inputs. And we define this function h as follows. And the barrier function condition for the system under attack is given in terms of this function h. And what we need to do is essentially verify if this inequality holds at each point on the boundary of the set S. But the question is, how can we check an inequality to hold on a continuous boundary which consists of infinite number of points? So in other words, we can ask a question, is it possible to evaluate the function h at only a finite number of sampling points and still guarantee safety? Or equivalently, can we find a parameter gamma and a finite set of sampling points on the boundary such that if we check this modified inequality with parameter gamma added on the right-hand side, just on the finite sampling points, finite number of sampling points, then the original inequality holds at each point on the boundary. It turns out that the answer is indeed yes, when we choose this parameter gamma as a product of the Lipschitz constant of the function h and the intersampling distance of the sampled point. Then satisfaction of this modified inequality at just those selected points indeed implies that the original inequality holds at each point on the boundary. So in this paper, we present our results for n sphere, but they can be generalized to other complex sets which are homeomorphic to spheres. So we sample the surface or the boundary of the sphere in such a manner that each point on the surface has at least one sampling point within the distance. We can show that the minimum number of sampling points required for satisfying this property is n plus 1. And we present some observations with respect to satisfaction of the required inequality and number of sampling points. First, if we choose a larger intersampling point distance, then we only require lesser number of points. And it means that we only need to check the required inequality at less points. On the other hand, if we choose a smaller dA, which would mean we need more sampling points to satisfy this condition, then this modified right-hand side, the gamma parameter would be actually smaller, and it would be easier to satisfy the inequality. As you can see from here, this parameter would become smaller, and it would be easier to satisfy this inequality. So there's a trade-off between ease of satisfaction and satisfaction at number of points. And finally, we can also observe that if this set, the set from which we can choose our adversarial signals, is smaller, then again, it becomes easier to satisfy this inequality. So based on these observations, we formulate an iterative algorithm to compute set of initial conditions. So we start with this data, which consists of the system dynamics, the function B, and the constraint sets. And we start by sampling the original boundary of the set S, and we check if the inequality holds at each point of the sampling set. If not, then first we reduce the size of our vulnerable input constraint set. If we can still not satisfy the condition at each point on the boundary, then we can increase the number of sampling points, again reducing this parameter here, and again check if the condition is satisfied at new set of sampling points. If that doesn't happen, what we can do is we can come inside the safe set at an inner sublevel set, and that would update the intersampling distance because this would be a smaller set, and it would be easier to satisfy the required inequality. And we can keep repeating this process until the algorithm converges and returns a C such that the negative C sublevel set is a viability domain, or a domain that can be rendered forward invariant. Now, using this set that we compute from our algorithm, we can propose a method to synthesize the state feedback law for secure input. So for that, we assume that our system is controlled affine, or it's linear in the control inputs. And for designing the feedback, we use all the inputs, the vulnerable as well as the secure inputs for performance criteria, which could be just reaching a goal set given as some zero sub-level set of a Lyapunov function. So for that, we use our nominal Lyapunov condition, and we use all of the inputs for satisfaction of the Lyapunov condition. But for safety, we only use the secure input, and we modified the robust control barrier function condition for under adversarial attacks, and we only use the secure input to guarantee that system does not leave the safe set. And we compute these sets, the set of initial condition and the set of allowable adversarial attack signals using our algorithms. And with that, we synthesize a quadratic programming framework to design input in real time. So this is our QP formulation, our quadratic program. Again, our control-affine system, and this is our QP where the first constraint is the input constraint for the secure input. The second inequality is the secure barrier function inequality. And third inequality is the Lyapunov function condition for the performance criteria. From the computed, using our algorithm, we compute this parameter C, and we can show that in this particular set, which is essentially the safe set, this QP is always going to be feasible. And the feedback designed as the optimal solution of this QP is continuous. And so we present a simulation example to demonstrate how our system actually works. So for that, we consider a nonlinear system where we have two inputs and three states, and we assume that the pair A comma B1 and A comma B2 are both controllable. So if any of the inputs are attacked, we can still control the system with the other input. And our safe set in this case is just the unit circle, and we have individual input constraints. And from our algorithm, we compute that 7.5 units of adversarial attack signal is tolerable by this system. And 3,000 sampling points on the unit sphere are sufficient for satisfaction of the safety inequality at each point. This plot actually shows that if we reduce the number of sampling points by increasing the inter-sampling point distance, then this particular inequality does not hold. And at 3,062 points, we are able to satisfy this inequality. And so in the first two attack signals, we choose the attack signals that do not satisfy the constraint that was computed by our algorithm. And we can see that the system trajectories leave the safe set. And so the system is actually not safe when the attack signal does not satisfy our condition. For the rest of the four attacks, we choose attack signals that satisfy our condition, and we choose different kind of attacks, such as maximum constant input, minimum constant input, sinusoidal input, and a square wave input with magnitude 7.5. And in all the cases, we can see from plots on the right-hand side that the system trajectory is linear in the units sphere at all times. So to conclude, we presented a robust control barrier function condition for provable security under cyber attacks. Then we presented a computationally efficient sampling-based method for computing a set of initial conditions from which safety can be guaranteed. And our future work includes designing a reliable attack detection mechanism using barrier functions so that we don't have to so that we can actually use the vulnerable inputs before the attack is launched, and then we can detect the attack and make the overall strategy much less conservative. Finally, we would like to extend this framework to multi-agent systems where the safe set will be actually time varying, and we would like to study how we can extend the sampling phase method for a time varying safe set. At the end, I would like to thank our sponsors who made this research possible. Thank you so much, and I'm happy to take any questions.